Welcome back to the specialized series on industrial artificial intelligence. Today, we are exploring a powerful machine learning method called the support vector machine, or SVM. Imagine a smart factory that produces high-precision metal parts for car brakes. Mia is a quality engineer in this factory. Her job is to decide whether each part is good or defective based on sensor readings like vibration, temperature, and surface roughness. At the beginning, the data looked clean. Most good parts were clearly on one side and most defective parts were on the other side. A simple straight line on a graph could separate the two groups. But as the factory produced more and more parts, the data became messy. Some points were borderline, some regions overlapped, and the simple straight line was no longer enough. So Mia has a question. How can I draw a boundary that separates good and defective parts as safely and confidently as possible, even when the data is noisy and overlapping? This is where support vector machines come in. You can think of SVM as a smart way to draw a line that does not just separate the classes, but separates them with a buffer zone. This buffer zone is called the margin. Let's build an intuition. Imagine you have blue dots for good parts and red crosses for defective parts on a 2D plot. There are many lines that could separate blue from red. Some lines pass very close to the points, and some lines leave more space between the two groups. SVM says, choose the line that leaves the widest gap between the closest blue points and the closest red points. That gap is the marginal plane. Why is a large margin good? Because in the real world, measurements are not perfect. Sensors are noisy, machines vibrate, temperatures change slightly. If your boundary sits too close to the data points, a tiny change in a reading can flip a good part to defective or the other way round. If your boundary has a wide safety margin, then small changes in the data do not change the decision so easily. In simple words, a big margin usually means a more stable and more reliable model. Now who decides exactly where this boundary is? This is the clever part of SVM. Not all data points are equally important. Only a few critical points, the ones that sit closest to the boundary, really matter. These are called support vectors. You can think of support vectors like the fence posts that hold up a fence. If you move a fence post, the fence moves. If you move a rock far away in the field, nothing happens to the fence. In the same way, if you remove a support vector and retrain the SVM, the boundary will change. If you remove a distant point, the boundary usually stays almost the same. So far we were lucky, a straight line could separate good and defective parts. But in many real problems like images, text, or complex sensor data, the classes are not separated by a simple straight line. They may form circles, spirals, or messy clusters that wrap around each other. SVM handles this using an idea called the kernel trick, but we will keep it high level. In the original 1D space and original 2D space, the data is not linearly separable, so any boundary would have to be a complicated curve. Looking at the figure, the kernel function maps these points into a higher dimensional space, where the same data becomes easier to separate, and a simple straight line or flat hyperplane can act as the decision boundary. You do not have to manually create all these new dimensions. The kernel function does the math behind the scenes, so SVM can still work efficiently. Popular choices include the linear kernel, the polynomial kernel, and the RBF kernel, which is good for flexible, blob-like shapes. Let's come back to Mia. Step 1, she collects data. For each part, she records vibration, temperature, and maybe roughness. She also has labels from experts. Each part is marked as good or defective. Step 2, she looks at a simple 2D plot, for example, vibration on the x-axis and temperature on the y-axis. She sees that many good parts are in one area and many defective parts are in another, but there is some overlap. Step 3, she trains a linear SVM. The SVM searches for the line that separates most good from most defective parts while making the margin, the safety street, as wide as possible. The points that sit closest to this street become the support vectors and define exactly where that line lies. Step 4, as the factory evolves, Mia adds more sensors. Now the pattern is no longer close to a straight line. She switches to an SVM with a non-linear kernel, such as the RBF kernel. In the original sensor space, the decision boundary now looks like a smooth curve that wraps around the risky defective region and keeps a comfortable distance from the good region. Support vector machines are used in many places, not just in factories. In text classification, they help separate spam emails from normal emails. In image tasks, they can help tell apart digits or objects. In medicine, they can help separate healthy cases from disease cases using scans or lab measurements. Why do people like SVM? Because they can work well when there are many features, they focus on a few important support vectors, and they can be adapted to simple or complex shapes just by changing the kernel. Of course, SVM is not perfect. On very large datasets, especially with complex kernels, training can be slow and memory-hungry. You also have to choose the right kernel and tune parameters like C and gamma, which can take time and experiments. Let's wrap up the main ideas. First, SVM tries to find a boundary that separates classes with the largest margin, like a wide safety street between good and defective. Second, only a few important points near this street, called support vectors, really define the boundary. Third, when a straight line is not enough, kernels let SVM work in a higher dimensional space where separation becomes easier, without you doing complex math by hand. For Mia in the smart factory, this means she can build a model that is not just good enough, but also confident and robust as her data changes over time. And you can start to see SVM as a tool that draws the best possible separating boundary with a safety margin using just a few key points and some smart math in the background. The future of industry is intelligent. Let's build it together. Thank you for watching.